Hello, everybody. Today we are going to talk about accelerated fatigue testing by removing some low damaging cycles from the time history. There is a specific process in TestLab Neo for doing damage based on time compression algorithm. Let's see how we can make use of that. Here we have a time history signal, which is an acceleration signal, and there are multiple cycles or events that are happening within this time history. We can see that it is an acceleration signal because it has a unit of meter per second square, and it is about 29 seconds long, as you can see from the x-axis on the bottom right hand side. We want to use that algorithm for time compression. We want to remove some load cycles but still preserve the main damage that can come from this time history. To be able to do that, we can use the TestLab Neo process designer. For doing that, we'll first put this data into the input basket. So I'll put it in input basket. And now I want to apply that process. And that is a process that is built in and it is available ready to use in TestLab Neo. And that comes with the main TestLab installation itself. This process designer is an add-in. So you can go to file and add-ins and add in this process designer add-in. It takes 19 tokens. And when I go here to the processing tab here at the bottom, I can go to open a process which I want to use. And you can see that there are many different processes. Some are which I made some processes, and those are the user level. And there are several other built-in processes that are available there in the central. So they come with the installation of TestLab. Now you can see that this process, it is red and not black like some other process. And that's because all the required add-ins for this have not been loaded. So let's see what add-ins are needed. So first I will load this process. So I select that process that I want to use and then click OK. And now it will tell me what are the add-in that is required for using this process. So here it says that it requires the rainflow based test definition, that one. And here this is saying that this requires the load data analysis. And so looks like those are the two which are needed for me here, the rainflow based test definition and the load data analysis. So I go here and load data analysis, I will load that in, and the rainflow based test definition. So I will add those two. And now we can see that all the boxes are not red anymore because all the required add-ins, they have been loaded in. Let's take a look at this process in more detail. It takes the input data, time history data, and then it does some time compression here, damage based time compression. There is an algorithm for that, and it goes through that, and then it does some statistical calculations, some rainflow calculations, and then it calculates pseudo damage, and it gives us some statistical results as well as some spectrum. There is some PSD also involved in that. So we'll be able to see the original as well as the compressed time history. I have this time data, so I want to go through this process. So I want to use as is, I guess, without making any changes. So we can go through the calculations to do that. But if I click on any particular method, which is part of this process in Neo, then we can find information about that particular method. And I can click on this and it says that this method is intended to remove segments from input signals, only contains load cycles below a certain threshold level. So there is a threshold level that we have to define, and whatever is below that threshold level, it will remove that and it will give us a compressed time signal. And that threshold is 80%. I have left it at the default 80%. So I have the input data, I have the process here, and I'm just click on this button run here on the bottom left hand corner to run through the process. When it does the calculation, initially it puts this results in this active analysis tab here. This is so that we can take a look at that results, and if we like the results, then we can accept the results and save them. If we don't like them, we don't have to keep them. So I clicked on this active analysis. Now I can see there are two time histories. One is the original time history and the other one is this compressed time history. So this is the original one. You can see that it's about 29 seconds long. And this is the compressed one. I can plot both of them. So original, we can see, is about 29 seconds long, and this compressed one is only about 3 seconds long. but we can see the maximum levels, they are the same. This algorithm removed this low damaging cycles and kept the main ones in the resulting time history. And we can look at the statistics that come out of this calculation. So here it is saying that the original, if it had 100% damage, then it is saying that this compressed time history has 97 or 98% of the damage. That is very good, right? So most of the damage captured from the original time history is also captured in this reduced time history or the compressed time history. We can see that the original was 28.3 seconds and the new one is 2.83 seconds. So that is 10 times faster. So we are accelerating the test by reducing the time length without compromising on the levels. What I mean by that is we are not artificially doubling or tripling the levels so that it does not introduce some unwanted behavior. And we are running the test 10 times faster. We can see the duration original is 100 and the new one is 10%. We are about 10% of the original time. So that means the test will run 10 times faster. And the maximum levels, you can see they are still the same. Minimum is also still the same. That is the beauty of this method, is that it preserves the original characteristics of the time signal, yet it accelerates the test. We can complete the test in a shorter period of time. Computes PSDs also, the power spectral density curve. So red is the original and the green is the new one. We can see the shape of the curve is exactly the same as the one before. The levels are slightly higher, we can see, of this compressed time history. I think that's just an artifact of the number of averages we do because of reduced length of the time history. This method, it does not produce any shifting of frequencies. See, that is one of the downsides of some other accelerated fatigue testing methods, is that they can lead to shifting in the frequency, but this does not do that. You can see there is a lot of benefits from this process. Reduced length of the time, it is accelerated testing, but it preserves the amplitudes of the maximum levels and it does not lead to any shifting in the frequencies. Now, one point which I would like to mention here is also that this original time history that we had was in acceleration. It is not in load. But if we think in terms of the damage calculations and the SN curves, S is the load and N is the number of cycles. But here we have an acceleration. So this is not strictly definition of damage. This is called pseudo damage because we are computing not from load, but from acceleration. So similarly, we can do the calculation from strain data also. You can see that finally we have the compressed time history and it is producing a result, which is what we desire. And I like what I see. It has reduced the time length by a factor of 10. I love that. And so I will accept that result. And I have that result which is stored here now. So the active analysis is become empty and it is now stored in here in the active project that I have. So we can see the original versus the reduced time history. There it is. That's the way it works. So thank you very much for watching the video.